Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 1319. Number of operations to make network connected. In this video, we're going to explain a solution based on UniFind, also known as disjoint set abstract data type. So in this problem, there are n computers numbered from 0 to n-1. Connected by Ethernet cables connections, forming a network where connections I equals AI BI, which means that there is a direct edge between or connection between computers AI and BI. So any computer can reach any other computer directly or indirectly through the network. So we are given an initial computer network specified by connections. We can extract certain cables between two directly connected computers and place them between any pair of disconnected computers to make them directly connected. So our task here is to return the minimum number of times we need to do this in order to make all the computers connected. If it's not possible, return -1. So here are three examples. In example 3, the output is -1. Here, this problem is very special because here we have 6 computers or 6 nodes, but our direct edges, the number of direct edges are 4. So 4 is actually strictly less than 6 minus 1. That is, 4 is less than 5. Therefore, it's impossible. For example 1, the output is 1, right? You can place this provides one solution, right? You can also use the connections between 1 and 2 to connect 2 and 3. This is also a choice. In other words, the choices are not unique. So in the second example, so if we look at this graph as a whole, so this 0, 1, 2, 3 are connected, and the 4 is not connected, 5 is not connected. Therefore, in the language of graph, so there are 3 different clusters. So to make them connected, we need 2 connections. So the output is 2. So I guess for this problem, the recognition or establishing the connection between the problem with graph theory or graph terminologies is essential for solving this problem. As for coding, so basically we need to find components in a graph. So typically there are 2 ways. One is traversal based. We can use breadth first search or depth first search to do the traversal. That's the one. Another option is to use UniFind. So it's this disjoint set abstract data type. So the UniFind method actually is very convenient. So in this video, we are going to present or explain a solution based on UniFind. Before we look at the analysis, actually we can also point out that so we need to look at these constraints, because these constraints form additional assumptions for this problem. Sometimes it gives us hint to do the coding. So here n is bounded above by 10 to the power 5. So 10 to the power 5 actually is a decent large number. Secondly, the connections is bounded below by 1 and bounded above by mean of this one and 10 to the power 5. So n times n-1 over 2 means that every 2 nodes are directly connected, right? So then the third one is that each element in the connections list is a length 2 list, and AI and BI does not equal. In other words, so we don't consider a self loop. So this makes sense because the computer itself, we can always regard it as connected to itself. So there are no repeated connections, and also no 2 computers are connected by more than 1 cable. So this is actually an important assumption, right? So with that said, we are ready to do the analysis. First, I'm going to make a correspondence between the terminologies in the problem and the terminologies in graph theory. Therefore, we can establish connections of this problem with graph theory. First, we regard each computer as a graph node. So this is one. And each element in the connection, we're going to regard it as a direct edge. So the problem asks all the computers being connected, which means that the graph is singly connected, right? So this is the correspondence. Next, let's explain the idea. First, we want to count the number of direct edges. So notice that we have n nodes. If the number of edges is less than n minus 1, and so in other words, it cannot form a connected graph. So it's impossible. So we're going to return -1. So this is one case, a very special case. So this actually corresponds to the case in example 3. And then the second choice, so if there are k connected components, and then we need k-1 operations to make them connected. For example, in example 2, so the connections given yields that the whole nodes as a graph, they have 3 connected components or 3 clusters. So we need 2 operations. And in the first one, so we have 2 connected components or 2 clusters. Therefore, we need 1 operations, right? So this is the idea. So then, as for implementing the idea, so there are 2 choices as we mentioned. So we can try traversal and we can try unifying. In this video, we are going to explain a unifying method. So here I will write here as an extension. You can try to solve it. Try traversal. So you can use breadth first based or depth first based. Both are okay. So another thing is that so we practiced quite a lot traversals or unifying. You can follow up in our channel in YouTube. With that done, let's implement the code. So actually the implementation is very routine. So first, because this n is already given, so I'm going to implement the union and find as a function, as functions inside this function here, make connected. So first, I'm going to define a dictionary called root. So I for I in range m, right? Range m means that the nodes are 0, 1 up to n minus 1. And then I'm going to copy this line and make some adjustments. So I'm going to write rex, and then the rex originally is 0. You can regard that the rec represents the cluster size for which I is in. With that done, so now let's implement the unified method. So here actually we can regard this step 0, right? Preparation or unified. So ADT, or if you like, right? Just some annotations. And then here I'm going to implement the find method first. So here I'm going to write with path compression. So it's just for acceleration purpose. So here let's define find. So it accepts a node. So here let's call it I, and then it's going to return the roots of this I. So here I'm going to use an iterative format. I'm going to introduce this result, and then we're going to check if result and the roots of result is the same. If not, then we are going to retrieve upwards. So basically we are going to set result to be roots result, and then we are going to return results. The reason is that after this while loop, or after we exit this while loop, result and the roots result will be the same. So we return result. So before we do this, actually here we can do some assign for the roots. So here you can understand that we copy this line and then we apply these roots on both sides once more. Right. So in other words, we set the roots of the root of results to be the roots of roots. Right. So this is a path compression. Right. So with that said, we finished the implementation of the find method. Now let's look at the union method. So the union method here, I'm going to union by rack. So by racks. So this also can help accelerate the procedure. So here I'm going to define union method, union function. It accepts 2 nodes. And then first I'm going to find the roots of ij. So it's going to find I, find j. So this line of code also explains why we first implement the find method. And then we're going to check if root I does not equals root j. We're going to do something. In other words, if root I and root j are equal or is the same, then we do nothing. So in this case, we are going to check the drags. If let's see, we want to have if, right? If rex root I is larger than or equal to rex of root g, it means that when we join the 2 clusters where I and j lie in, so this root I represents a larger cluster. So we're going to set the roots of root j to be root I, and then we combine the 2 clusters. This way, the rex of root I will be increased by the size of the cluster represented by root j. Therefore, we do increment by this. Otherwise, so we do the same thing, but in a reverse direction. Let's copy these 2 lines, and then we're going to change this to be root I. We set the roots and the roots of root I to be root j, and then increment the rex of root j by that of root I. So this is the implementation for union find. So in practice, sometimes we don't need to use such fully fledged function or methods, but here we just implement it for demonstration purpose or just for practice. So up to now, we finished the first step. So next, we are going to check or incorporate with problem logic. First, I'm going to get the m. Let's see, just it's not absolutely necessary to assign a name, but let's do it just for clarity. So we get connections. So this is the number of not m. Let's see, n edges. So this may be better, right? Because we know n is already given as the number of nodes. So first, I'm going to check if n edges is strictly less than n minus 1. And then we're going to return -1. In other words, it's impossible for the odd node to be a singly connected graph. So with that checked, this corresponds to B1 here. Let me write this. And then we're going to look at B2, right? So for B2, we need to get the clusters. So basically, the cluster, each cluster is represented by its delegate or the roots of all the nodes inside that component. Let's write a simple function to do this, just for so let's see, get n clusters or n components. Write n clusters to save several characters or typing. So here, let's define this function clusters. So it accepts no argument. So basically, we want to do count. So this is very simple, right? We can check the length of the set. What's set? So it's a number of different roots, right? So it's find I. for I in range M. So this actually gives the number of clusters. Let's do this. So for clarity, I'm going to introduce the n clusters. N clusters equals n clusters. Let's see. Let's just do this. Return n clusters. So this -1. So this would be 2. I guess for now we finished the coding part, and this piece of code forms a solution format to this problem. So before we move forward or make comments, let's first do a check. Wrong. What's the problem? That's so here the thing is that we haven't do the unit operations yet. So let's also change this one to be step 1, not step 0. So here let's do this. So for ij in connections, then we do union, right? And then we can get this B1, and then we can get the clusters after we do this, right? So now let's do the check. Yeah, it passes this test case. Now let's look at the generic case. Yeah, it passes all the cases. So here I would like to mention that this function actually gets the number of clusters of. So we should call this function after we do the union operations. And also, just to give you more method or functions, we also can get the clusters specifically. So here we can write functions get clusters. So here we can do this. So I can have a collections default dictionary. I'm going to use that as the container. Then I'm going to iterate. So for node and let's see, for u and v in roots items. So notice that v is a parent or the root of u. Then first I'm going to find the root of all this of v. And then what I'm going to do is to root add u, right? So this way we get the clusters. Let's see, we return d. So here for the test case, we can actually print out the clusters. Print. So here is d, right? So no, not d. Here is get clusters. Let's test this. Yeah, for this example, so this is for example 2, I guess. So this is the 3 clusters. 0, 1, 2, 3 are connected, and 4 forms a cluster, and 5 forms a cluster. And in this case, we return 2. So here, let me comment out this one, and also I'm going to comment out this part. But if you like, you can have this. And then we just do a final test to make sure it's correct. Yeah, I guess that's it for this specific problem. So you are welcome to check out other videos in my channel, especially in the UnionFund playlist. There are many practices using UnionFund. Personally, I feel that the UnionFund method is a very useful method. It can help address a number of different kinds of graph problems. So with that said, I guess that's it for this video. Thank you.